Hey everybody, in this video we are going to show a very simple, very basic how-to or application of the difference quotient, which is also segueing into applying the limit definition of a derivative. At the very end of the video, I will even take it that one extra step further and use it to not only find what we call an average rate of change, but to actually find what we call the derivative by applying a limit. To understand what this is and why, please check out the introduction video, which will be the first video on the playlist of understanding calculus. All right, and it'll be in the description box and it'll be in the thumbnail at the end of the video, where all the videos on this topic will be on that playlist as well as others. So let's get started. So this is all being tied into composition of functions. And hopefully everybody knows that the composition of functions is probably most commonly recognized with something looking like f of g of x. And this is where we take one function and plug it into another function everywhere that outer function had an x, or whatever that variable may have been, right? So everywhere you have an x, it's sort of like your little stand-in or your placeholder, and you're going to plop in this entire other equation. So it's like when the big fish eats the little fish in like those little cartoons, you know? So it's going to look something like that. But before we can do what we call the difference quotient, which we see right here, we want to just make sure we're properly doing f of x plus h. Now, h might be delta x when you see it presented to you in another situation, but for right now, for simplicity, I'm going to use h as much as I want to use delta x. So let's get going. If f of x, which is given, equals x squared, then f of x plus h means that everywhere you have an x, we're going to fill in the value of x plus h, okay? Now, if I grab the highlighter just to embellish this a little, you know, for impact, there's your x, and we're plopping in x plus h right there in place of x, okay? And that's what finds us the f of x plus h, right? And we're going to need that down over there, okay? Now, I would say we're not done yet. It's very important that we know how to properly expand this. And for the love of math, if you write down x squared plus h squared, just leave. Goodbye. Click off this video. Or if you want to be better, then stay. So x plus h squared means you're taking x plus h, and when you square something, you multiply it by itself. Back in ancient times, when arithmetic was really hard, geometry was easy, and when they wanted to square a number, say they wanted to, well, they didn't call it squaring yet, but say they wanted to multiply a number by itself, like 3 times 3, they made a box, a shape, with dimensions of 3 by 3, and that's why we use like the x as by for our dimensions. So they make a little 3 by 3, and then they count up the boxes and they get 9, right? But actually, part of the issue why this was such a big good time with the visual math was because they were doing more so Roman numerals and whatnot. Gross. And they couldn't really use x probably because x is a Roman numeral too, so I don't know what the heck they used. Maybe they were the ones that used the dot. I'm not even sure. So you guys can check me on that, fact check me. But then they counted up the boxes and they get 9, and that shape is what we commonly refer to as a square, hence us calling it 3 squared. So there's your little cute lesson of the day. You're welcome. So when you are squaring something, you are multiplying it by itself, and it's very important that we do that here. So we're going to do that and use the mnemonic device FOIL to get this going along. So x times x is going to equal x squared, or x to the second power. X times h is xh. Then h times x is also xh. And just running in the same order, h times h is h squared. And then my outer and my inner end up being like terms. So we combine them and we get x squared plus 2 xh plus h squared. And there we have it. This right here is the f of x plus h. So we got x squared plus 2xh plus h squared. And for those of you who are familiar with Pascal's triangle, row 2 in Pascal's triangle has the numeric values 1, 2, and 1. And I'm going to refer to row 2 because this is a binomial to that second power. So we have 1, 2, 1. You take that first thing and you put it to that second power, to the first power, to the 1, and the last guy to the none. So there's nothing there. Please don't even write it because you're going to mess up and probably just leave it as x. And even that x to the 1, we could just call x. And then you take the second thing, the h, and you do the same thing in reverse. H to the 2, h to the 1, and h to the none. So we will leave that. And then when it's a plus sign in the parenthesis that you're expanding, you make everything a plus sign. It will always be a plus sign in this type of situation. If it were a minus sign, this would stay positive and you would alternate minus, plus, ba, ba, ba. That's a little crash course right there for you guys on how to use Pascal's triangle to expand a binomial, and you'll see it again in the 2 videos later in the playlist for x to the 3rd and x to the 4th doing this exact same thing. But for now, I'm going to erase that. Okay, anyhow, let's move on to part 2. So part 2, or example 1b, is now using this, and we're going to find the difference quotient, DQ, not Dairy Queen. So we're going to find this difference quotient, which is difference subtraction, quotient division. There we go. We're going to determine that right there. So f of x plus h, I don't know why I started writing f, I already know what that is. That is x squared plus 2xh plus h squared. Now I'm going to do minus. I'm going to make it a really heavy minus to really exaggerate it. Now f of x, well, what the heck is f of x? F of x is the original function for this particular scenario. So that original function, x squared, right there, right? F of x is equal to x squared, and that's what we're going to plop in after. So then we have minus x squared, and that is all over h. So there we have your f of x. Here we have our f of x plus h at the beginning part. Now again, we're not quite finished. We need to clean it up, because if you watched the introduction video, this little h down there, right? This little h is sort of like, he's the devil, guys. He's really that little purple devil emoji guy, you know? And we're just like, get the heck out of here, because really, ideally, we would absolutely love if h could pretty please equal 0. But being in the denominator the way he is not allowed to equal 0. What a monster. So we want him to cross out, go away, bye-bye, so that we can plug in 0 for h. Well, let's see what happens as we organically, naturally kind of clean this up. Looking at our numerator, I have x squared minus x squared. Adios, guys. That leaves me with 2xh plus h squared all over h. Now, you cannot just slice and cross out those h's. I will have a stroke. What we could do is factor out an h from both terms on top. We have 2x plus h. Oh, I don't like how squashed that is at all. So let's go down here. So I'm going to factor out an h, and that leaves me with 2x plus h all over h. And now that little monster in the denominator, we're going to be able to get rid of him, right? We're going to be able to cross out this h and this h. Bye-bye. That leaves us with, for now, the answer of 2x plus h. And that's beautiful, and we love that. So did we determine this? We sure did. It is that right there. However, I told you in the beginning of the video I would follow through. And if we were to do a little more with this, like you'll see in calculus, we want to take this and, how I mentioned, this guy's the devil because we want h to really equal 0. Go watch that introduction video. If I can plug in 0 for h now, well, I'm going to do it. So what's 2x plus 0? That answer is 2x. So this answer in purple down here is what we call the derivative, by using the limit definition of a derivative. This is the derivative of x squared. And normally you would use some limit notation. You would write limit as h approaches 0 out front the entire time. And once you got rid of the little devil by crossing this out, well, now we're allowed to use something called direct substitution, where I can actually fill in 0 for h and get my answer for my derivative of 2x. You're welcome. Hope you loved it. Thumbs up if you're happy and you know it. And bye for now. Adios.